Okay, we're starting. Continuing 3.1. Let's do a small recap of what we spoke about in 3.1. We started talking about some derivative properties. One of which was the constant factor rule. How do you differentiate a constant times a function? What did the rule say?
You can factor the constant out.
You factor the constant out and just differentiate the function. This is called the constant factor rule. So if you know how to differentiate the function and you have a constant times the function, you automatically know how to differentiate a constant times the function. I don't think I identified this for you, but why this works, it's pretty easy to see. If your y is a constant times this one, your y prime would be, using the definition, the limit as h approaches 0, of c times f of x plus h minus c times f of x all over h. It's a limit rule that we can factor constants outside of limits, so I can actually factor that constant c out. So that's c times f prime of x. Okay. So constants are never really, a constant factor is never really a big deal when we're doing derivatives. You can just always factor them out and just differentiate them. That's going to help us do a lot of nice problems. So that was one property that's going to make our lives easier. Another property was the sum property, the sum rule. That says if you differentiate a sum of functions, how do you differentiate a sum of functions? You can differentiate one at a time. So it turns out derivatives distribute across products. The derivative of a sum is just the sum of the derivatives. So you can actually do that. You have a bunch of things being added together. You can differentiate each one individually, add them together, and that's your answer. And so that was called the sum property. How we know we can do that is, again, it falls in line with the limit definition. So if I define a function to be the sum of two things, then my y prime would be the limit as h approaches 0. I'll plug in x plus h in the function, then minus the function all over h. And of course, I could rearrange this. Take the f of x plus h and the minus f of x, put those together. Divide by h plus, oh, that guy's not in. I can separate the g's and then separate the fraction across the numerator. We know we can do that. And this, of course, is the derivative of f. Plus, that's going to give us the derivative of g when we take the limit. So the derivative of a sum is just the sum of the derivatives. We can know that by the limit definition. Now, we also spoke about the derivative. Well, I just mentioned it to you. I didn't prove it. I'm not going to prove it. The derivative of the exponential function. Also, you want to recall the derivative of the exponential function. What was that? Derivative e to the x, yeah?
E to the x.
It's also e to the x. Right? Which has a function, you know, without a constant factor being involved. It's the only function besides 0 that is its own derivative. Right? No other function has that property. It's a very special property, and it's very useful for calculus. We also spoke about what we call the chain rule, which we didn't prove either, but it's just the rule that we need to know. This talks about how to differentiate composite functions, and how was that? Yeah?
So prime of f with like g regular inside times prime of gx.
Right. So it's the derivative of the outside function multiplied by the derivative of the inside function. That's basically the chain rule. And we did an example of that. But let's actually use this right now to sort of generalize this rule in a bit. So here's an example or a question. What is the derivative of e to some function? Right, so not just e to the x, e to some function. So instead of the x in the power, I plugged in a function into the power. Right, so if y is equal to e to the g of x, then my y prime is going to be, what do you think the answer is going to be? Yeah?
E to the gx times g prime of x.
It's going to be e to the g of x times g prime of x. You might say why? Because of the chain rule. Right? Here, I had a composite function f of g of x. It was kind of like my f was e to the x and my g was, g of x. And I took this guy and I plugged it into that guy. Right? So that then my f of g of x would be e to the g of x. Right? So this is a composite function. I have something plugged in that's potentially not just x, and so I have to apply the derivative rule. I differentiate the outer function, but for the exponential, the derivative of the outer function is literally to do nothing. It is its own derivative. But because it's not just an x, there's a function plugged in, I have to multiply by the derivative of the inside function. Right? So that's a rule. This gives us a generalized version of the exponential rule. It says if you have derivative of e to any power, I'm going to call it u, the derivative is u prime times e to the u. So that leaves us with combining these two, the chain rule applied to the general exponential yields that derivative. Let me just illustrate with a simple example, but we're going to move on because we'll do tons more examples later. So for example, if I wanted to differentiate e to the x cubed, what would that be equal to? Yeah?
3x squared times.
Well, I don't think we did x. We did x squared.
So 2x times
Right.
x squared.
Take derivative of the power, which is 2x, times the original function. Right, so the derivative of e to the x squared is 2x e to the x squared. Right, and that's for the exponential. Now this rule is important because I'm going to use it to derive another rule. Well, all the rules are important, really. You should have them all memorized. Everything I put in a box should be memorized. So now here's a question. Another fundamental function, especially if we are talking about e to the x, we might want to talk about its inverse. What is the derivative of ln x? Does anyone know the answer? Derivative of ln x? Yeah?
Is it 1 over x?
It is 1 over x, but how did we know it's 1 over x? Let's figure it out. Let's say I set g of x equal to ln x, right? So my goal is to now find g prime. How would I go about finding g prime? Well, because I don't know anything about the log function, I don't know how do I find the derivative of log function. I don't know. If I knew that, I wouldn't ask the question. So one thing you might want to do is if there's a log in your expression and you don't know how to deal with it, you get rid of the log. How do we get rid of logs?
Raising it to the...
Raise both sides to the e. Use exponentials to kill logs. So I can do this. So what I have now is I have e to the g of x equals, these guys kill each other, and that's x. So now e to the g of x is x, meaning if they're the same, their slopes have to be the same, so I can differentiate both sides. If they're the same function, they must have the same slope. How do I differentiate e to the g of x? Boom. Literally just did that, it's right there. That would give us e to the g of x times g prime of x. Derivative of x is 1. We derived that with the limit definition last time. And so now, the goal is to find g prime. So I'm just going to solve for g prime. So this would mean that g prime of x is, I can just divide both sides by e to the g of x. I don't have to worry because the exponential we know is never 0. So I can divide both sides by that. And so that's 1 over e to the g of x. But what is e to the g of x? In this problem that we just said. It's just x, it's right there. E to the g of x is x. So this is really just 1 over x. So if my function is the ln x, the derivative is 1 over x. This is another rule. The derivative of ln x is 1 over x. Again, a very important rule. You don't know how to derive it, but you do need to know this rule, right? Derivative of ln x is 1 over x. We're going to be learning a bunch of rules that we kind of need to know by heart in order to be able to do more difficult things. And that's one of them. So we need to know the derivative of a constant times a function is just a constant times derivative of the function. Derivative of a sum is just the sum of the derivatives. Derivative of e to the x is just e to the x. Derivative of ln x is 1 over x. Derivative of e to the u is u prime over u. I can generalize this rule as well using the chain rule. So if I have the derivative of ln, let's say it's not just x, it's a whole function like u. Right? So once you have something plugged inside that's not just x, you have to apply the chain rule, which basically says differentiate the outer function, but the derivative of the outer function is just 1 over the thing that's being logged. But then you have to multiply by the derivative of the inside function. And so that gives us a generalized version of this rule. Derivative of ln u is u prime over u. That's the chain rule version for this rule. If you have to remember one of these, if you don't like memorizing a bunch of formula, I would memorize this one. Because this one actually covers that. If my u were just x, x prime would be 1. And so I would still get that 1 over x. Right? So this rule includes that rule, but it's a lot more general. I can do a lot harder things with it. So for example, if my function was ln, what do we know how to differentiate? X squared plus 1. What is my derivative? Yeah?
2x over x squared.
Right, so it's going to be the derivative of this over the thing itself. So it's whenever you're trying to find the derivative of ln of something, it's the derivative of the thing over the thing itself. Now the derivative of x squared is 2x. Derivative of 1 is 0. So that's my guy. And notice that on the inside I just used the sum rule, that the derivative of a sum of things is just the sum of the derivatives, so I just differentiate one at a time. We know that the derivative of any constant is 0. We prove that using the limit definition. So that would be the derivative. Alright, so if that's your function, this function will give you the slope at any point. With what we have so far now, I can prove one of the main rules of section 3.1, the power rule. Exponentials and logs are very important functions as well, but polynomials in general are important functions, and anything that looks like a polynomial. So let's answer that question. We're going to make it slightly more general. What is the derivative of x to some power? Where n is a constant. Now we did prove some of these, right? I know what the derivative of x is, that's when n is 1. We know what derivative of x squared is, We know what derivative of 1 over x is, which is n equals minus 1. You know what the derivative of radical x is, which is when n equals a half. But now we want a general rule that can deal with any power, even including the ones that we haven't done yet. So let's derive it. Set u equals x to the n. Now it turns out the power is kind of what I don't really know how to deal with if it's not one of those numbers. Because sure, if it was x squared, we could expand the f of x plus h definition, and if it was radical x, we know we can multiply by the conjugate. But for general numbers, like if this was 1.378, how do you deal with that in the limit definition, right? So the power is kind of confusing here. So I want to actually get rid of the power, not have to deal with the power. How do I take a power out of play? How can I get rid of powers? What construction do we have to like, if I have a power, let's not deal with the power anymore. A log. Logs can get rid of powers. The log of something to a power is just the power times the log, right? So I can turn a power into a multiplication. So in other words, what I'm going to do here is I'm going to log both sides. Now the log rule says I can bring the power down in front here. So if my u is x to the n, my ln of u is just n ln x. Now if these two are the same, their slopes must be the same, so I'm going to differentiate both sides to find the slope of each side. How do I differentiate ln of u?
It's 1 over here.
No. It's u prime over u. How do I differentiate n times ln x?
N over x.
It's n over x. N is a constant here, so the constant factor rule applies. Leave the constant alone, differentiate the function. Derivative of ln x is 1 over x. So this is just n times 1 over x, or n over x. So let's rewrite. My u is x to the n. The point is to find the derivative of x to the n. So what I'm really interested in is the u prime. So I'm going to solve for that u prime. And that's just going to be n over x times the u. But what is u in this case?
It's x.
U is x to the n. So now I can just substitute that. This is n over x times x to the n. Or in other words, this is n times x to the n over x. And what is that? What is x to the n divided by x? Laws of exponents. Yeah.
X to the
N minus 1. The power in the bottom is 1, and so we can use the laws of exponents. Dividing things on the same base, you subtract the powers. So that's my u prime. In other words, the derivative of something that looks like x to the n is nx to the n minus 1. This is a very important rule. It's called the power rule. The derivative of x to the n is equal to nx to the n. I don't want that. Derivative x to the n is equal to nx to the n minus 1. This guy is very important. We even give it a name. It's called the power rule. Called the power rule for derivatives, because integrals have their own power rules, so you can emphasize. At this point, every time I say the power rule, I'll be referring to this guy, but there are other power rules out there. So this is the power rule for derivatives. It is the rule that tells us how to differentiate x raised to some constant power, no matter what the constant is. Right? I never assumed anything about the constant. So this can be 1, 2, minus 7, 3.9, pi, radical 11. Doesn't matter what that number is, I know how to differentiate that function, right? So with this, I know how to differentiate any polynomial because a polynomial is just kind of a sum of terms like that. I know how to differentiate any radical because radicals are just when these guys are fractions. And I know how to differentiate things that are neither of those. So this is like x to the radical 2. That's not a radical, it's not a polynomial, it's something else entirely. But I can deal with all of those with the power rule. So let's do some examples with the power rule. It's a very important rule. It's one of the main rules. Besides e to the x and ln x, it's one of the main rules in 3.1. It's a very important rule. You should have it memorized. Everything I put in a box so far should be memorized. So let's do some examples. In fact, let's go over the things that we proved using the limit definition with the power rule. It turns out we could have used the power rule to derive all of those guys. So let's say I needed to find the derivative of x. Right? We kind of know the answer is 1, but that's because we went through the whole power rule thing, the whole limit definition thing, and derived that. But it turns out the power rule can be applied here. Just think of that as x to the 1 power. So according to the power rule, bring the power down in front and subtract 1 from the power. So this is 1x to the 1 minus 1. So the power comes down, subtract 1 from the power. That's how you differentiate x to a constant power. What is x to the 1 minus 1? That's just 1 times x to the 0, so that's just 1. So that tells us that the derivative of x is 1. The limit definition wasn't too bad for that, but it was longer than that. We also could look at the derivative of x squared. Now remember, to derive this, we use the limit definition. We have to have x plus h squared minus x squared. We have to expand, kind of plugging in h equals 0. Turns out with the power rule, it's easy peasy, because this is just x to the n. Bring the power down in front, subtract 1 from the power. The answer is 2x. So the derivative of x squared is 2x. You could get that in a couple seconds with the power rule. We also looked at the derivative of radical x. Right? And that guy we had to multiply and divide by the conjugate and simplify and all that stuff. Turns out with the power rule, that's also not so bad. The trick is to first write it to look like the left side, meaning x to a power. So how can you rewrite that? Radical x is?
X to the 1/2.
X to the 1/2. So now I can just apply the power rule where my n is a half. Bring the half down, subtract 1 from the power. So this is a half x to the minus a half. And so that's your derivative. By the way, that's the same guy we had from last time. Just so you can see it looks the same. Negative power just means you can put in the denominator. That's a law of exponents. X to the half is just radical x. And then you multiply these guys, you get 1 over 2 radical x, which is what we derived last time. It's exactly the same. But we did it with obviously a lot less work. The power rule can really simplify things here. We also spoke about the derivative of 1 over x. Plug that into the limit definition. We got a complex fraction. You have to multiply and divide by the LCD and do all these simplifications. We can also do that with a power rule with very little effort. How would we do that? Yeah?
Wasn't that just x to the negative first?
Right. So we rewrite it. So, and this is going to be a principle that we are going to be using throughout the class. You want to apply the rule, you need to rewrite whatever you're working on to look exactly like the rule. So I want to use the power rule. The power rule says it has to look like x to the n, right? Meaning, do not apply the power rule unless what you're looking at looks like x to the n. So if I have this, I want to apply the power rule, I need to rewrite it to look like that. Right? So now it's like my x to the n, where my n is minus 1. And the rule says, bring the power down in front and subtract 1 from the power. So that gives me minus x to the minus 2, or minus 1 over x squared. We derived that, but it was a lot more painful. we can also derive the fact that the derivative of any constant is 0. This one's a little bit more tricky. You kind of have to put something there that wasn't there before. Just realize that c is really c times x to the 0, because x to the 0 is 1. That's a law of exponents, so I can put in 1 in this sneaky way. So that's going to be the derivative. The constant can factor out, but I'm now going to differentiate x to the 0. So this is just a power rule where my n is 0. So that's just c times 0 x to the 0 minus 1. But I'm multiplying them all by 0, so the whole thing just becomes 0 anyway. So with the power rule, I can see the derivative of a constant is 0. And so with the power rule, we just kind of re-derived all these rules I told you in the time it took to derive like one of them. Right? The power rule is going to be very quick. It's a very powerful technique. Anything you can write as x to a power, which is a lot of things in this course, you can use the power rule to differentiate. Do another example. Find y prime if your y is equal to x cubed plus 3x squared plus 12x minus 1 over x cubed. We're going to find the derivative of that guy. Now let's just take a moment of silent contemplation and kind of imagine what this would look like going through the limit definition. You'd have to compute, obviously, f of x plus h all cubed, right? So that's going to distribute x cubed plus 3x squared plus 3x squared h plus 3xh squared plus h cubed. You're going to have to expand this guy with x plus h. Then you're going to have to do that all in the denominator. That's going to be a huge complex fraction. You're going to multiply and divide by the LCD. The LCD here would of course be like x cubed plus 3x squared h plus 3xh squared plus h cubed. It's not going to be a fun time, is the point, right? You're going to do this, you're going to spend the entire test doing a problem like this. But with the power rule, it's actually not that bad. It's actually pretty quick. So because, one, you can see that each of these guys here, they're in the form with the power rule. Well, this guy kind of is messing up. He's a fraction. How can I deal with that guy?
X to the negative 3.
X to the negative 3, right? So I could rewrite this at first. 3 squared minus 12x minus x to the minus 3. Right? Now all of these guys, all the functions look like x to the n. I'm adding a bunch of things together, but the sum rule says to do that, just differentiate each one at a time. Derivative of the sum is just the sum of derivatives. Some of these guys have constants in front of them, but that's also not a problem because I have the constant factor rule. Derivative of constant times the function is just the constant times the derivative of the function. And so we know how to differentiate all these functions. We know how to differentiate the whole. So now when I'm taking the derivative, the first thing I do is apply the constant factor rule. That says leave the constant alone, then find the derivative of the function. Derivative of x cubed is, it would be 3x squared by applying the power rule. 3 comes down in front, subtract 1 from the power, gives you the power 2. Plus, constant factor rule, leave the 3 alone, and differentiate x squared. I didn't say anything wrong, that was right. Okay, so the 2 comes down. Subtract 1 from the power, so you just get power 1. Minus 12. Differentiate x, this is x to the 1. Bring the 1 down. Subtract 1 from the power, you get x to the 0. That's just 1, so that stays here. That's a minus. This is x to the n. Bring the minus 3 down. And subtract 1 from the power, you get minus 4. So that's the derivative. Of course, we can rewrite this a little nicer just by multiplying these numbers here. That's 15x squared plus 6x minus 12 plus 3x to the minus 4. that's the derivative. Anyone interested can use the limit definition and compare how long it would have taken you to figure that out. And really, these intermediate steps here, like this one, eventually you'll be able to skip that, because in your head you'll know that the 3 is going to come down, multiply the 5. You'll immediately be able to know that that's 15. But that takes a little bit of practice. So that's the power rule. Very, very important rule. And there are many situations that it can help us deal with. Let's continue. That kind of ends all the theory we need for 3.1. We're skipping 3.2, so we're now moving on to 3.3. In 3.3, we're going to deal with 2 other very important rules. One is called the product rule, and the other is called the quotient. So let's justify the need to even look for more rules. Why do we need anything? It looks like the power rule is pretty powerful. Why do we need anything else? Here's the reason. Our goal here is to figure out how to differentiate something like one function multiplied by another function, and how to differentiate one function divided by another function. Now, you might be tempted to sort of think that this ends up being very straightforward, and you might guess that the derivative of f times g is just the derivative of this times the derivative of that. I mean, that's how it works with sums, and that's probably how it works with products. It turns out you would be wrong. It's actually not that easy with products, right? If it were, I would have told you that property back in the last section. Products are a little bit more complicated. It turns out that that's not true. And it's not so hard to see this. I can give you a very simple example. We know what the derivative of x squared is, right? That's 2x. If I rewrote x squared as x times x, what would happen if I differentiate each part of this function separately and then multiply them together? Derivative of x is what? 1 times derivative of x, 1. I would get the derivative is 1, which I know is wrong, right? There's no way this works, right? So the derivative of a product is not the product of the derivatives, right? It's not like sums. With a plus sign, yeah, you differentiate each piece, stick them together. It does not work with multiplication. So products are kind of weird and tricky themselves. That's why you need a whole product rule. Similarly with divisions, it doesn't work either. Right? So you might guess that the derivative of f divided by g is going to be f prime over g prime. Turns out that that's also wrong. That's not how you can differentiate a division. And you can see that again by knowing that the derivative of x squared is 2x. But if I rewrote that, let's say I rewrote x squared as something like x cubed over x. If I differentiate the top and differentiate the bottom separately, what would I end up with? What's the derivative of x cubed?
3x squared.
3x squared by the power rule. What's the derivative of x?
1.
1. So this would tell me that derivative of x squared is 3x squared, which I know is wrong. Right? So there's a need to look for rules where we deal with products and quotients. Quotient is just a fancy word for the result of a division. Right? So when we're dividing two things or we're multiplying two things, it's not clear exactly how to go about finding the derivative. Because the brain dead way of thinking you just differentiate each part of the thing, it doesn't work. It's not true. Okay? And there are very easy examples you can point to that tells you that's not true. So let's find out what is the truth. Let's search for truth. How do you differentiate a product? figure it out. Set y equals f of x times g of x. And sometimes when we don't know how to deal with something, we just go back to the definition. Y prime would be the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x, all over h. So that would be our derivative. So now, here's the tricky part. You kind of do this trick that it's not exactly strange to mathematics, but because when you're completing the square, for example, you do this kind of thing. You add and subtract the convenient expression to simplify things, right? So it's like when you're completing the square, you add and subtract half the coefficient of the x term squared. We're going to do that here. So with this guy, I'm going to add and subtract a certain thing. I'm going to subtract f of x times g of x plus h. And I'm going to add f of x times g of x plus h. So I'm adding 0. I'm not changing the value of the expression because I'm just adding 0 in a very convenient way. And you might say, why would that be convenient? Well, let me show you. I can now split these two fractions. I can now split this into two fractions. So this would be f of x plus h, g of x plus h, minus f of x times g of x plus h, over h, plus f of x times g of x plus h, minus f of x g of x, over h. Let's simplify these fractions. How do you simplify these fractions? Well, how do you simplify any fraction? You factor. So I'm going to factor this, factor the top and bottom. And so to factor, one thing I would do is look for common terms. In this case, g of x plus h is a common term. Let's factor that off. So let's pull that g of x plus h out to the right. And so what I would have left here is f of x plus h minus f of x over h. Similarly here, now my f of x is a common term, I can factor that off. And I would be left over with g of x plus h minus g of x over h. Great, let's go through now. We know from limit properties that the limit of a sum is just the sum of the limits. So the limit, I can take the limit of this and the limit of that. We also know that the limit of a product is the product of limits. So I can take the limit of this times the limit of that and the limit of this times the limit of that. So really the limits can go through the components. So let's do that. What's the limit as h approaches 0 of this? What is that? What's the limit as h approaches 0 of f of x plus h minus f of x over h? Can you see? Limit as h approaches 0 of f of x plus h minus f of x over h. What's that?
It's the derivative of f.
It's the derivative of f. That's the definition of the derivative. So that part just becomes f prime. What's the limit of g of x plus h as h approaches 0? Well, you just plug in h equals 0 because you're not dividing by 0 or anything like that. So that just becomes g of x. Plus, h approaches 0 does not affect this because it doesn't have any h's in it. So that's just f of x. What's the limit as h approaches 0 of g of x plus h minus g of x over h?
It's the
Derivative of g by definition of derivative. And that's the formula for differentiating a product. Differentiate the first one, leave the second function alone, plus you leave the first one alone, differentiate the second one. This is called the product rule. So it turns out if you're differentiating something that looks like two functions being multiplied by each other, this is how you need to differentiate that. derivative of f times g, where these guys are functions. Right, technically you should be writing f of x and g of x, but I'm getting too lazy. What's this? You don't need to know how to derive it, but you do need to know the rule. I just kind of want to show you that these rules don't come out of nowhere. There's a reason why they have to be that way. So there's a reason why. Why couldn't I just differentiate that one, differentiate that one? That's why. It has to fall in line with the definition we know to be true. Why you gotta make it hard, Jhevon? I'm not making it hard. This is what it has to be. Like I had no choice. That's the rule. You differentiate one, you leave the other one, plus you leave the first, differentiate the second. This is a very important rule. It has a name. It's called the product rule because you use it to differentiate products. Obviously not all products. If one of your functions happen to be a constant, just use the constant factor rule. Although, to be, notice that this is consistent. If your f happened to be a constant, its derivative would be 0, so you'd only get the constant times derivative of the function anyway. But you don't really have to think about it that way. So that's the product. Let's do a simple example. Suppose I ask you to differentiate something like x times e to the x. So that's your function, x times the exponential. How would you differentiate that? Use the product rule. So how would you apply it here? Yeah?
Differentiate x, then plus e times e to the x, plus differentiate e to the x times x.
Yeah. So especially when you're just starting out, it's hard to, it can be difficult to see it at first. So what I would recommend is that you literally just mark on your paper who you're choosing to be who. So you can say, I'm going to call this guy f, and I'm going to call that guy g. First you have to recognize when two things are being multiplied. You have to realize, hey, this is a product. So what you do is you name each component of the product. Name this part f, name that part g. And you know that the answer you want to get to is f prime times g plus f times g prime. And you can write that out, right? And then you apply it right below, right? So you just literally write down each thing below the rule. So if my f is x, what is f prime? 1. Times g. What is g? Well, it's e to the x. Plus, now there's my f. What is f? Well, it's just x. Times g prime. What is g prime? I know my e to the x is g. What is the derivative of e to the x? E to the x. Right, so you literally just plug each component in below the formula that you memorized, and it falls in line. It's a template. All these rules I'm giving you, think of them as templates. So this is basically e to the x plus x e to the x, which in most contexts will be fine. Sometimes you'll go further and simplify this. You factor out the e to the x, which will give you e to the x times x plus 1. The context in which you would factor something is either one, if I ask you to do it, like I might say, oh, find this and simplify or and factor. Or there are some times when we're going to want to be able to set the derivative equal to 0, and to figure out where is this equal to 0, you would actually factor to figure that out and apply the factor property, the 0 factor property. But that's the answer. That's how you differentiate something like x times e to the x. Any questions on that? Let's deal with the second situation, the division of functions. That didn't work either in the just to differentiate each piece. So how do we actually figure out how to divide, how to find the derivative of a division? It turns out, because we know how to deal with multiplication, we kind of automatically know how to deal with division. Because multiplication and division, they're inextricably linked, they're kind of almost the same. For example, dividing by 2 is the same as multiplying by a half. So that operation you can literally think of as a multiplication or a division, you just have to change your notation a bit. So knowing how to deal with multiplication gives us a good head start on how to deal with division. So I don't have to go through the whole limit definition again. Let's just use what I know about products by just rewriting. Let's say I wanted to figure out the derivative of f over g. Right, what is that? Here's what I would do. Rewrite this to look like a multiplication, because I know how to deal with multiplication. How would that look? F times 1 over g, which is not a very efficient way. We can rewrite that, the second part. G to the minus 1 is how I would rewrite that. So in other words, a division, I can think of it as kind of like a product, right? And this is going to help me derive a formula for it. I'm going to rewrite this a little bit just to emphasize certain things. F of x times g of x to the minus 1. I kind of want to emphasize that my g is kind of like an inside function here. So now, all I'm going to do is apply the product rule. So this is going to be f prime times this plus f times. Now we're going to have to figure out the derivative of this guy. How do we figure out the derivative of that guy? Yeah?
Chain rule.
We would need the chain rule. How would it apply here? So it's not like you have x to the minus 1. You have a whole function plugged in for x. So that's the first thing you need to realize. Okay? So it's a function to the minus 1. So what does the chain rule say we do?
Differentiate the outside.
Differentiate the outer function, which is just the minus 1 power. Apply the power rule, right? So you bring this down, subtract 1 from the power. So that would be the first step. So this would be minus g to the minus 2. And then what? Multiply by the derivative of the inside times g prime. So to differentiate this part, I needed the chain rule, but we already know that. And that's the derivative, but let's actually try to write that in a nicer form here. Sorry, this is g to the minus 1. So this guy would really be f prime over g. This would be a minus. Here I have my f times g prime, and I'm divided by g squared, because that's g to the minus 2. So I get those two fractions. I can combine this into one fraction by creating a common denominator. So now my common denominator is g squared. And in the top, I would have f prime times g minus f times g prime. We have just derived the quotient rule. This means the derivative of f of x over g of x is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. This is called the quotient. Now it's very important that you memorize this rule. For one, you should know that the order matters. Let me put this in a box so I know. And notice here, this is called the quotient rule. very important rule. And notice that the order matters here. Right? Because of the subtraction sign. So if you put the wrong guy first, you get the wrong answer. Right? 3 minus 2 is not the same as 2 minus 3. It's kind of, you don't really want to make that kind of mistake, because remember, here you're finding a derivative, so that means that could mean the difference between increasing and decreasing. So you want to tell someone, so how are our profits looking? Plus $2 million a day, sir. It's a very different situation from minus $2 million a day, right? So you don't want to mix that up, okay? So that's called the quotient rule. The order matters, and while I was writing down, you heard me say a phrase. That's kind of how I remember the quotient rule even to this day. I literally say the phrase in my head. It was the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. There are other mnemonics. A common one that I hear students say all the time is low D high minus high D low over low squared. Anyone ever heard of that?
Yeah.
Yeah, so there's that one. So that's where you kind of think of it as the high and the low. So it's low D high minus high D low over low squared. The same kind of idea. You take the derivative of the top function times the bottom minus the top function times the derivative of the bottom over the bottom squared. And you get that low D high minus high D low over low squared. But I hear people mix up with that a lot of times. Low D high, high D low. Hey, if you memorize it that way, that's better, but I rather use the words top and bottom. There's no, I can't kind of mix that up. Because the other one is too much like a melody. Low D high, high D low. You know, with top and bottom, it's not really a melody. It's kind of like, that's what it is, that's the phrase. Okay, so you do have to memorize that, and you need to make sure you memorize it in the right order. If you want to make your life a little easy, you can just make sure that you memorize the product rule in this order, and know that for the quotient rule, you change the middle sign and then divide by g squared. However you do it, do your thing. I don't know how you memorize stuff, but memorize it. That's very important to remember. So let's do an example here, and then I also want to look at some situations where something like the product and quotient rule, while it might be valid to use them in these situations, it's overkill, it's too much. And it might introduce extra errors. So let's do an example first, just a quick example, simple one. How would you differentiate x divided by e to the x? So we looked at x times e to the x, let's look at x divided by e to the x. How would we do that? How do we do that?
Could you rewrite it as x times e to the x to the minus 1?
You could do that, but I want to specifically apply the quotient rule. I'll talk about that later.
You just click it.
You just plug it in, exactly. But you just have to make sure you name your things properly. So in this case, in the product rule, it does not matter who you name what, who's the f and who's the g, whether you name the one on the left f and the one on the right g, or the one on the left g and the one on the left f. In the product rule, it does not matter. In the quotient rule, though, the order matters. So if you're memorizing this formula, you have to make the top guy the f, the bottom guy is the g. The order will matter. So you know that you want to write down f prime times g minus f times g prime over g squared. And now you plug those in, right? That's your template. So you go one at a time. So you go one at a time and you just plug them in. Boom, 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 boom. Okay, so you first plug in f prime. What is f prime? Well, it's 1, because my f is x, so that's a 1. Times g. G is just e to the x. Minus the f, which is x, times g prime, My g is e to the x, the derivative of that is just e to the x. Divided by g squared. My g is e to the x, so it's just e to the x squared, which is e to the 2x. But let's bring this a little further and simplify it. In the top, e to the x is a common term, so I'm going to factor that out. Then this can cancel with one of those. So the derivative of that function is 1 minus x over e to the x. As Victor was suggesting, he was thinking of rewriting this. Let me just quickly write that down, even though I wasn't really planning on doing that. You could do, if you see something like x over e to the x, you can rewrite it as x times e to the minus x and apply the product rule. So you could do derivative of 1 times the second plus v to the first times the derivative of the second. Here you'd have to remember that the derivative of e to the u is u prime times e to the u, so that introduces a minus 1 here. And so that's just e to the minus x e to the minus x. And that's also the derivative. One way you can see that, that's the derivative. This is just e to the minus x. You factor that out, you get x to the minus 1, and then e to the minus x you can bring to the bottom. So ultimately you'll get the same answer. So you can do that. I have known students who have, I don't know, moral reservations from using the quotient rule, we should call it. So they just don't like using the quotient rule. So they like rewriting as the product rule and then applying that there. That's totally fine. It's a personal preference. We sort of derive the quotient rule by doing a manipulation like this in the first place. So it's always a valid thing to do type of. But personally, I don't find an issue with either way. There are some times where actually doing anything too fancy is just not worth it. So let's look at that. Or not to use the product and quotient rules. And these are sort of, it's not like it would be wrong to use them here, but these are sort of recommendations. So that is in terms of like being a student in a calculus class and having to do these things on a test. There are situations in which you might want to apply the product rule, but probably you shouldn't do that. So let's talk about the product rule. Try to simplify first is the idea. So for example here, so you always have to remember your algebra. You'll always need to remember your algebra for calculus. So if you see a function like x times the radical of x and you want to find the derivative, right? Technically you could do the product rule here. That's your f, that's your g, but it's kind of going to be overkill because you'd have to do the product rule and it's split into two things and you have to make sure that you simplify properly for whatever reason. It would be much nicer to just simplify this guy using the laws of exponents, because you have x to the 1 times x to the half. You can just add the powers to get x to the 3 halves. And then differentiating that is the power rule, which is super easy. Bring the number down in front and subtract 1 from the power. So that's your answer. It's easier to apply than the product rule. There's less room for error because you have less terms to have to simplify. So always try to apply algebra rules before you start to apply calculus, apply easy things first. That's also a general rule of thumb towards math things. Before you start thinking of these complicated, sophisticated things, try the simple things first. If you look at the quotient rule, so if you see something like this, like your y equals, so again, try to simplify. And in this case, and so an example of that is if your y equals something like this, 5x cubed minus 2x plus 3 all over x or something like that. This is a division. Technically you can apply the quotient rule, but technically that would be overkill because this is something you can simplify pretty easily and use a much simpler rule, right? Because there's a single thing in the denominator, just divide it into each thing, right? So just realize that this is the same as saying that this is 5x squared by dividing that by x, minus 2 dividing that by x, plus 3x to the minus 1. And then I can apply the power rule. So this would be 10x, that would be 0, minus 3x to the minus 2. Right? So if you have a single term in the denominator, try to divide. You won't always be able to do this, but in the cases that you can, you should do it because it will cause a lot less work. A lot less room for error, a lot less terms to be moving around. So with all the derivative rules, sometimes you just do a quick scan to make sure that, okay, everything is in its simplest form. I can't simplify anything before taking a derivative. And then you try to take a derivative. So here and here, I would simplify them, and it actually, I can use a simpler derivative rule to figure them out. There are a couple other cases in which the quotient rule is just overkill. If the numerator is a constant, or the denominator is a constant, don't use quotient rule. Honestly, it's a waste of time, and I've seen students make silly mistakes here. Like, while doing the quotient rule, somehow, it's very common for students to forget that the derivative of a constant is 0. I don't know why they do this, but I see it all the time, and they happen to be doing the quotient rule. They forget, oh, the derivative of the numerator is going to be 0 because it's a constant. They forget that for some reason. So if numerator is constant, what you should do is I'd rather you rewrite and use chain rule. By rewrite, I mean just bring the denominator up, put it to the negative power, use a chain rule. It'll be quicker and easier than doing the quotient rule. If the denominator is a constant, you can essentially just leave it alone. You can kind of just ignore it. And differentiate the top. So you differentiate the top, leave the bottom alone. So let's see some examples of that. So for example, if my y was 1 over the radical of x squared plus 1, I want to differentiate that. So you might look at that and like, it's a division. Quotient rule. No. Slow down and think about this. Think about this. Do you really want to use the quotient rule? No. Right? Look at the rule. The quotient rule is huge. You have to have mnemonics to remember it and stuff. It's much easier to, so I see that I would notice top is constant. No quotient rule. To be clear, it's not wrong if you use the quotient rule, but I've just seen students try to apply the quotient rule in situations like this and they get it wrong, just because they have more stuff to do with. the trick would be to just rewrite this as that, right? It's the same thing. And now I can just apply the chain rule. Differentiate the outer function, so I bring the power down, leave the inside intact, subtract 1 from the power, then I multiply by the derivative of the inside. That's the derivative. 2's can cancel, so I have something like minus x over square root of x squared plus 1 cubed. If I had, for example, y equals something like 3x squared plus 5x over 7, right? So in this case, the denominator is a constant. It turns out the derivative is going to just be differentiate the top, 6x plus 5, leave the bottom alone. That's your answer. Why does that work, by the way? Can you see why that works? Yep.
Because 1/7 would be constant.
It's 1/7, right? This guy, I can think of it as just 1/7 times this. And the constant factor rule says, just leave the constant alone, differentiate the function. So I can do that. So if your denominator is a constant, just ignore it, differentiate the top, right? If your numerator is a constant, bring the bottom up, use the chain rule. In either of these cases, algebraically, you'll spend less time than in the quotient rule. So we'll stop there. Technically, I told you everything you need to know, but I want to do a bunch more examples, so the homework is not due on Tuesday, even though I will be giving you a quiz on it. You probably want to look over some of the problems. But the homework for 3.1, 3.3, and 3.4, I'll make that due on Friday. So that's, I think it's the 9th. So definitely still look over things because I will be quizzing you on it, but the homework isn't due until Friday. Because I want to do a lot more examples. So out there, I'll see you guys on Tuesday.